Okay, so if you look at this format problem, it says the flight of the rubber band you fling across the room can be modeled by the function. If you look at that function right off the bat, you should be saying to yourself, okay, that right there is intercept form. So the very first thing that I know about it is the x-intercepts. It says f of x is the height of the rubber band in feet. So this is your height in feet. And then it says that the x is the distance that it travels in feet. So I always get an idea of what my graph looks like first before I even start trying to answer the questions. I know from this form that my x-intercepts are going to be at 9.8 comma 0 and negative 2 comma 0. Well, if you think about that, the one I'm going to graph is the 9.8 comma 0 because this is, hopefully isn't going to go backwards, and that negative 2 is saying a negative 2 feet is meaning 2 feet backwards. From there, you can figure out your vertex and your x-intercept. So your vertex, if you know your x-intercepts, is right in the middle. So if we add 9.8 and negative 2 together and divide by 2, we get 3.9. So that's the x-coordinate of our vertex. If we take 3.9 and we substitute it back in to our original function for x, you're going to end up getting 10.443. So our vertex is at 3.9, 10.443. So this is just a rough sketch. And I label everything just to make my life easy when I'm going to answer the questions. And then the last thing we need is our y-intercept. Well, your y-intercept is when x is 0. So if we substitute 0 into our function for x and do so correctly with your parentheses and everything in your calculator, then you are going to get 5.88. Okay, so this is at 5.88. So the rubber band follows that path. So now that we have an idea of what the graph looks like and we know what everything means, we can answer the questions. How far does the rubber band travel? Well, if it says x is the distance the rubber band travels, then I'm asking for the x value, so the x-intercept, so that's 9.8 feet. Okay. What's the domain? Well, the domain is your x. It's how far it's traveling. So that's going to start at 0. 0 means you're holding on to it. And it lands on the ground at 9.8 feet. That's going to be included because it is actually the end of the graph. Okay, that's not like you're increasing, decreasing where you don't include it because it's not a max or min. Our vertex, we already did the work for. That's 3.9, 10.443. And what does it mean in the context of the problem? Well, you have to think about what does x represent and what does y represent. X is the distance the rubber band traveled, and y is the height. So after the rubber band traveled 3.9 feet, it reached its maximum height. You guys, that's the key word that we're looking for. Of 10.433 feet. You guys, if you don't have maximum there, then you're not saying that the vertex is anything special compared to any other point on the graph. But we are looking for maximum. Okay. All right, what x value maximizes the function? When you think maximum, you think vertex, so the x coordinate of the vertex is 3.9. Where is it increasing? Okay, so obviously this is linked to your domain. You're not going to say negative infinity because this is a contextual problem. This starts increasing from the x value of 0. Remember, increasing and decreasing, you are focusing on x values only until it hits 3.9. And then that's its max, so it's technically not increasing and it's not decreasing, so you don't include it. At that max point, it starts decreasing again, so 3.9 until it hits the ground at 9.8. Then it stops. This is a contextual problem, so I don't care about that infinity and negative infinity. In the grand scheme of things for this problem, this only traveled 9.8 feet, so that's what I'm focusing on, from 0 to 9.8. Okay. So what we're going to talk about today is we're going to start talking about average rate of change. You guys, this is not something new for you, which is why we're doing the video. So if it looks very familiar, that's good. Okay. Average rate of change is how much a quantity changes, obviously, over a specific interval. Okay, now last year you guys talked about linear and exponential. Linear functions have a constant rate of change. They never have a different rate of change no matter which 2 points you pick. Now, exponential and quadratic are different because they have a rate that's going to change, and that rate will depend on which interval you choose. So both exponential and quadratic depends on the interval chosen. Okay. So remember, rate of change, you've seen that M before. You might think slope, okay, for your rate of change from last year. It's change in Y over change in X, or your formula is Y2 minus Y1 over X2 minus X1. Okay, so for this first problem, we're going to talk through a couple different things. We actually are not going to answer this question down here, so you can cross it off on yours. Okay, I'm just going to make a little bit more room to write. You guys, if you are a big writer on these notes, make sure you write kind of small because I'm going to be doing a lot in each space. So this says data on a certain car shows that its gas mileage can be modeled by a linear function. The car yields 45 miles per gallon when driven at 40 miles per hour. So if you're going 40 miles per hour, you're getting 45 miles per gallon. And then if you're going 80 miles per hour, you're getting 25 miles per gallon. So the function that represents this situation is f of x equals negative 1/2 x plus 65. And the question that's posed here says, what is the rate of change of this car's gas mileage? Well, hopefully you can look at this from last year and say, well, that means m is negative 1/2, and then that's my rate of change. But you need to make sense of that. And so when you're looking at this problem, you say to yourself, okay, I have x and I have y, and it doesn't state which one's which, so we kind of need to think about this. We have two variables that are going on. We're talking about miles per gallon and we're talking about miles per hour. So how fast you go and what kind of gas mileage you're getting. So you need to think way back to x and y being independent and dependent, which aren't words we've used this year. But your independent variable is always x and your dependent variable is always y. So if you look at the two variables we're looking at, miles per hour and miles per gallon, you need to say to yourself, okay, well, which one depends on the other? How fast I go, that's what I'm controlling. That's my independent variable. And then that is going to dictate how many miles per gallon I'm getting. So that tells me x is going to be my speed. That's your independent. That's what you're controlling. Y is going to be your miles per gallon, or your gas mileage, in other words. Okay. So your gas mileage is depending on how fast you're going. So we have two pieces of information we know. We know that when you're driving 40 miles per hour, sorry, I'm going to get rid of that. There we go. All right. When you're driving 40 miles per hour, then you're getting 45 miles per gallon. When you're driving 80 miles per hour, you're getting 25 miles a gallon. So what that means is the faster we go, the less gas mileage we have, which is why we have a negative slope here. If you thought about that in context or in graph form, this is my speed and this is my miles per gallon, so your gas mileage. Oh, sorry. My computer's notorious for that. One sec. There we go. Okay, so we'll go by 20s here and we'll go by 10s here. So I'm at 40, 45, and then I'm at 80, 25. So we are going down. Sorry, that's a bad graph, but you guys get it. So you're decreasing. So what does that mean? That means as your speed increases, so as we get farther along our x, our y is decreasing. So the more you speed, the lower miles per gallon you're going to earn. So in the context of this specific slope of negative 1/2, remember it's change in y over change in x, you are losing 1 mile per gallon. One mile per gallon for every 2 miles per hour, you increase your speed. Okay, so if you increase your speed by 10 miles per hour, then you're going to lose 5 miles per gallon. Remember, it's constant, that rate of change. So if I increase by 20 miles per hour, then I'm going to lose 10 miles per gallon. Okay, if I'm doubling my miles per hour, then I'm doubling the loss of miles per gallon. But we're losing because that's a negative slope. Okay, so we're going to do that a few more times today. That's in context, and now we're going to look at it a little bit more algebraically. So if you look at the back of your notes, you're going to start seeing a couple different things. We have quadratics, we have linears, we have tables, we have graphs. Okay, this isn't on your notes, but last year you found the average rate of change for linears and exponentials because that's what you worked on, and these are the two that you looked at. Well, if you have a line, you have a constant rate of change. I can pick any 2 points on that line, so I could pick those 2 orange points or the 2 green points, and either way, the difference between them is the same. So therefore, you get a linear constant rate of change. So here, if you look at an exponential and quadratics are going to be the same, let's say I pick these 2 green points, and that's the interval I'm looking at. Well, that's going to have a different rate of change than if I pick these orange points. If you look at those lines drawn from the green points to the orange points, they do not have the same slope, so they do not have the same rate of change. So depending on the interval that you choose, you're going to have a different rate of change. So if you look at this first one, it says calculate the average rate of change for the function f of x equals x squared plus 6x plus 9 between x equals 1 and x equals 3. Well, we need to know when x is 1 and when x is 3, what is y? So the function when x is 1 is going to be 1 squared plus 6 times 1. So this is a lot like when we were finding the y coordinate of our vertex, right? Same problem. 1 squared is 1. 6 times 1 is 6 plus 9. And we get 16. So that point is the point 1, 16. Then we're going to do it again for f of 3. For the function when x is 3, we have 3 squared plus 6 times 3 plus 9. Notice I'm not picking up my calculator. So 9 plus 18 plus 9. And that's going to get you 36. 9 plus 18 is 27, plus another 9 is 36. So that's the point 3, 36. Well, now we have 2 coordinates, so we can find our rate of change using our formula. So our formula is change in y, so remember to stay consistent. I'm going to do 36 minus 16, so then I have to do 3 minus 1. Remember, whatever coordinate you start with in your numerator, you have to start with in your denominator. So that is 20 over 2, which gives me a rate of change between those 2 points of 10. Okay. All right, for number 3, it says use a graph to calculate the average rate of change of the function. So A says what's the average rate of change between x equals -3 and x equals -2. So get your bearings here a little bit. These are actually scaled by 0.5, so that's what each line is representing. So at -3, we're here on the graph. So at -3, my y value is a +2. And at -2, my y value is a -1. Now, you could use a formula here, or you can say, okay, well, let's just focus on change in y over change in x. My change in y from here to here, well, I went from 2 to -1, so my change in y is -3, and my change in x, and it's negative because we went down, my change in x is a +1, so I have a rate of change from -3 there. You can use the formula and have the same exact answer, it doesn't matter. Here, now we're looking at the average rate of change between x equals -3, which we know is the point -3, 2. Okay, so this same point. But then we want it at -0.5, so if you look at -0.05, we are up at 5.5. Okay. So again, you can use the formula, or you can say to yourself, okay, my change in y from 2 to 5.5 is 3.5. My change in x from -3 to -0.5 is a positive 2.5. So your rate of change is 3.5 over 2.5, which is, if you were to divide that, 1.4. Okay. So if you look at this, which one has a greater rate of change between those 2 points? So even though this graph goes down and back up, it's a quadratic, you're looking at the linear, the linear change from one point to the other. So from here to here, and then we did from here to here. So technically the greater rate of change here would be part A. The negative is just implying that you have a decrease or a negative slope, but you're really looking at that number because this is changing faster than this because the absolute value of -3 is 3. So that's what you want to focus on. That negative is just telling you you have a negative slope or positive slope. It's almost like direction, but it doesn't mean that you're increasing slower because you have a negative slope. Okay, you just want to know how fast you can get from point to point. So if you look at number 4, this might be a good one, you guys, if you want to pause the video right now and work through it, read it, and then it's the same idea as what we just did number 3, but read it, pause it, and then hit play again and see how you did. But for this function, it's in vertex form. So we need to figure out all of the y values that correspond to these x values because it says what's the average rate of change? Is it greater between x equals -1 and 0 or between x equals 1 and 2? So we could graph this and get an idea of what's going on, or you can substitute values in. So for when x equals -1, g in this case of -1, since our function is g, is -1 minus 3 squared minus 2. So -1, you get -4 squared minus 2. -4 squared is a positive 16 minus 2 is 14. And then g of 0 is 0 minus 3 squared. Sorry, guys. 0 minus 3 squared minus 2. So you get -3 squared, which is 9. 9 minus 2 is 7. So the 2 points you're looking at there are -1, 14, and 0, 7. So if we calculated our rate of change there, we would have 7 minus 14 all over 0 minus a -1. So we would get -7 over 1 or -7. If you look at the other set of points, we have g of 1. So 1 minus 3 squared minus 2. That's -2 squared minus 2. So 4 minus 2 is 2. And then g of 2 is 2. Oops, that's sloppy, sorry. G of 2 is 2 minus 3 squared minus 2. So you get -1 squared minus 2. So -1 squared is 1, minus 2 is -1. So your points there are the points 1, 2, and 2, -1. So if you find your slope between those 2 points, you have -1 minus 2 all over 2 minus 1. So -3 over 1, which is -3. So this is similar to what we talked about on the last question, because this question is asking which one has the greater rate of change. Well, over here, we had a rate of change of -7 between the points. Here, we have a rate of change of -3. So your greater rate of change is technically between x equals -1 and x equals 0, because even though -7 is a number, is less than -3. That negative is just implying that they both have a negative slope, but this is changing faster because 7 is bigger than 3. So the greater rate of change, sorry, I kind of ran out of room here. So you can think about it linearly if you were to draw a greater rate of change. Sorry, guys. Slightly annoying. Is between x equals -1 and x equals 0. So if you were to think about it, like we were talking about here, you would want to think of slopes. So it would kind of look something maybe like this, but your steeper slope would be the -7 versus the -3, which is why that's your answer. Okay. All right, last one. Now we're just going to use a table of values. So this says, what is the average rate of change between x equals -0.75 and x equals -2.5? So you just need to go and pull those pieces of data off of your table. So -7.5 and -2.5, and use your formula. So m equals, change in y would be 8.44 minus 3.44 all over -0.25 minus a -0.75. So you're really going to look like you're adding there. So you end up with 5 over 0.5. So that rate of change would be 10. Okay. For part B, you guys do me a favor. We're going to change that x equals 0 to x equals 0.25. Okay. So those points would be at -1, 0, and 0.25, 10.94. So our slope there is going to be 10.94 minus 0 all over 0.25 minus a -1. So you end up with 10.94 all over 1.25. So your slope ends up being 8.752 when you calculate that. So you could look at that again. Your greater rate of change, if we were to ask you to analyze that, would be between -0.75 and -0.25 rather than -1 and 0.25. Okay, so you're going to use that formula. And remember, sometimes you don't need the formula. Sometimes you can calculate it graphically in order to do your homework tonight.